Greetings to Dr. Intan. We are here to present our group assignment 3. My name is Angappan and these are my group members Kanapathy, SUJENDRAN and SAILESH KAUSHAL. This assignment focuses on the identification of two unidentified samples, 13 and 15. Sample 13 thought to be a metal type material, while sample 15 is thought to be a tile type material. From the physical observations, we decided to perform different forms of material characterization examination including Raman, XRD and FECM EDX analysis for sample 13, whereas for sample 15 we decided to perform FTIR, Raman, XRD and FESEM EDX analysis. This is the standard procedure that we plan to identify the unknown material of sample 13. The process flow starts by identifying the suitable material characterization techniques. This sample basically looks like a piece of metal, and we conducted some research on material characterization techniques that might be used to identify the unknown material. There are few material characterization techniques that might be used, including XRD, Raman, and FESEM EDX analysis. After identifying suitable material characterization techniques, we proceeded to send the sample 13 for analysis one by one. Before sending the sample for analysis, we cut sample into small pieces which is 1.5 cm length using hand grinder. Then sample 13 was first sent to the XRD analysis, followed by Raman analysis and lastly FESEM EDX analysis. After completing all the material characterization analysis, we collect the results from each analysis and proceed to further investigation to determine the material of the sample 13. And this slide shows the standard procedure to identify the unknown material of sample 15. The process flow starts by identifying the suitable material characterization techniques. This sample basically looked like a piece of tile, and we conducted some research on material characterization technique that might be used to identify the unknown material. There are few material characterization techniques that might be used is XRD, Raman, FTIR, and FSEM EDX analysis. After identifying the suitable material characterization techniques, we proceeded to send the sample 15 for analysis one by one. The sample was first sent to the XRD analysis followed by Raman analysis. After completing the first two material characterization techniques, we crushed the sample 15 into powder using pastel and mortar. This step is crucial to easing the next two material characterization analysis. We divided the crushed powder into two equal quantities and sent it to FESEM EDX analysis and FTR at the same time. After completing all the material characterization analysis, we collect the result from each analysis and proceeded to further investigation to determine the material of the sample 15.
Next, I'm going to present the standard procedure to conduct material characterization using FESEM EDX. The picture illustrates the field emission scanning electron microscope with energy dispersive X-ray spectroscopy, FESEM EDX model SU5000. This slide shows the list of material characterization analysis which can be done using FESEM EDX. Firstly, elemental identification. The EDX technique can identify the elements and their relative concentration by analyzing the characteristic X-ray emitted when the sample is bombarded with the electron beam. Secondly, the surface morphology. FESEM EDX image present high-resolution views of the surface morphology and topography of the sample. Next is phase identification. FESEM EDX can help in determining the presence of various phases or compounds in a sample. Then, the elemental mapping. FESEM EDX can help in determining the presence of various phases or compounds in a sample. Besides, the quantitative analysis. FESEM EDX enable quantitative analysis of elemental composition by constructing the intensity of X-ray peaks in the spectrum to known standard. Lastly, the elemental composition. The EDX element in the image offer data about the sample's elemental composition. Next, I'm going to explain about the FESEM EDX sample preparation. The first step is cutting and mounting with the cutting tools such as a diamond saw or wire saw. The second step is mechanical polishing. This process can be done by using coarse abrasive materials such as grinding paper and abrasive disc. The next step is the chemical etching process, which is an optional process. Chemical etchants such as needle and killer's reagent can be used. The next step is a sample cleaning using solvents such as acetone or ethanol. Then, the next step is to use the conductive coating for non-conductive samples. The typical conductive material is gold, palladium, or platinum. The last step is the sample labeling. Next, I'm going to explain the characterization using FESEM and FESEM EDX of unknown sample 13. Using FESEM, we are able to see the surface morphology of the sample. From this image, we can observe the blunt, rough, and uneven surfaces are present. Next, we are going to analyze the spectrum, which shows the elemental analysis of unknown sample 13. From the spectrum, we can observe that nickel has the highest concentration, followed by carbon, tin, iron, and etc. Next, from the elemental composition table, we are able to identify the percentage of primary elements present in unknown sample 13, which shows nickel percentage at 41.8% and carbon percentage at 51.2. Next, I'm going to explain about the possible material of unknown sample 13. From the morphology, spectrum, and elemental composition analysis, we are able to shortlist some type of material that could possibly be sample 13. The table shows the four types of material, which are stainless steel, cast steel, carbon steel, and nickel-based alloy that could possibly be sample 13. Next, I'm going to explain the characterization using FISM and FISM EDX of sample 15. Using FISM, we are able to see the surface morphology of the sample. From this image, we can observe the blunt, rough, porous, and uneven surface are present. Next, we are going to analyze the spectrum, which shows the elemental analysis of unknown sample 15. From the spectrum, we can observe that oxygen has the highest concentration, followed by silicon, aluminum, iron, zirconium, and so on. Next, from the elemental composition table, we are able to identify the percentage of primary element present in the unknown sample 15, which shows oxygen percentage at 55.5, silicon percentage at 19.9, and aluminum percentage at 8.1. Next, I'm going to explain about the possible materials of unknown sample 15. From the morphology, spectrum, and elemental composition analysis, we are able to shortlist some type of material that could possibly be sample 15. The table shows the two type of material, which are ceramic tiles and porcelain tiles that could possibly be sample 15.
Next, I'm going to present the standard procedure to conduct material characterization using XRD. The picture illustrates the X-ray diffraction equipment, which is the Rigaku Miniflex 600-3 model. Now we go on to the list of material characterizations analysis using XRD. First, we can identify the crystal structure, we can conduct phase identification, phase quantification, and also observe the crystallinity of the material. Next, we can do a crystallographic orientation and texture analysis, microstrain and defects, and also residual stress analysis. Next, I'm going to explain about the XRD sample preparation. The first step is grinding using pestle mortar or mechanical grinder to grind the sample into a fine powder. Next, the sample is mixed with an inert binder or grinding agent. After that, the sample is mounted using glass slides, quartz plates, and specialized sample holders composed of materials such as aluminum or quartz. And apply a small layer of powder sample into the holder, making sure it's uniform and spread covers to the appropriate area. To produce a smooth and flat surface, use abrasive sheets or polishing products. For sample 13, which is a metal sample, there is no grinding required. Instead, the sample is cut, polished, and cleaned before being placed into the XRD analysis equipment. Now I'm going to explain the characterization using XRD of unknown sample 13. The peak position at 44.71059 degrees corresponds to the presence of iron at the 111 plane, and peak position at 52.1043 is of iron at 200 plane, which shows the beta phase in iron. The diffraction peak of copper is identified at 49.66165 degrees, which corresponds to the presence of copper at the 200 plane, and the peak position at 72.86643 degrees is of copper at 220 plane. The phases of copper are indicated by the alpha phase for both copper and also copper-based nickel alloys. Stainless steel alloys are typically comprised of iron as the base metal, with nickel, chromium, and carbon as acting as the primary alloying elements in varying quantities. For this, the primary alloying element is chromium, that should be present and to be considered as stainless steel, but it is not present in sample 13. However, copper is present with alpha crystals, which indicates that there is a possibility that the sample 13 is a nickel-copper based alloy with nickel as the base metal, with iron, copper, and carbon as the alloying element. Now we move on to the characterization of unknown sample 15. The phase of aluminum trioxide positioned at 104, 113, and 116 planes between the peaks of 20 and 80 degrees. Next, the peaks of silicon oxide, which is positioned at 100, 121, and 231 planes, also positioned between 20 and 80 degrees. And finally, the diffraction peaks of iron oxide, which is positioned at 200, 208, 212, 121 and 430 planes, also between the angles of 20 and 80 degrees. And through the XRD analysis of sample 15, the presence of distinctive compounds which are essential building blocks for formation of ceramic and porcelain tiles such as aluminum oxide, silicon oxide have been identified. However, the presence of iron oxide in the XRD results proves that the sample cannot be porcelain tiles as they primarily compose of refined clay minerals which contain oxygen, aluminum and silicon, zirconium, which are typically not present in porcelain tiles. And the possibility of the material of sample 15 is that it is a ceramic tile.
Now I am going to present the standard procedure to conduct material characterization using Raman spectroscopy. The picture shows the UniRAM 3500 Raman machine model. This slide shows the list of material characterization analysis using Raman. First, Raman can be used for molecular identification and also structural characterization. Next, Raman can be used to conduct surface and interface analysis. Raman technique also can be used for compositional analysis. In addition, Raman also can be used to conduct chemical bond analysis. Lastly, Raman is also used to conduct material characterization in different states. Now I am going to explain about the Raman analysis sample preparation. The first step is sample cleansing using solvents. The second step is subject selection. The next step is the sample preparation method using matrix material like KBR. The following step is drying process followed by laser selection. Then equipment calibration is performed and the last step is the data analysis. Next, I am going to explain the characterization using Raman for unknown sample 13. Using Raman, we are able to see that the composition of the sample. From the spectrum, the vibration modes appeared from the range of 200 cm-1 to 2100 cm-1. From the Raman spectra peaks, we can find out the possible material of unknown sample 13. From the composition analysis using Raman spectra, various alloy constituent elements can be seen in the Raman spectra for nickel-based alloy. These Raman spectra analysis could possibly confirm that sample 13 is a nickel-based alloy. Next, I am going to explain the characterization using Raman of unknown sample 15. Using the Raman, we are able to see the composition of the sample. From the spectrum, the vibration modes appeared from the range of 200 cm-1 to 2100 cm-1. From the Raman spectra peak, we can find out the possible material of unknown sample 15. From the Raman spectra, possible ceramic material at the region can be seen. The calcium phosphate and both kaolin and feldspar peak were present. These distinctive peaks correspond to the composition of ceramic tiles. Thus, this could possibly confirm that sample 15 is a ceramic tile. Next, I am going to present the standard procedure to conduct material characterization using FTIR. The picture shows the JESCO FTIR 6100 model FTIR machine. This slide shows the list of material characterizations used using FTIR. First is identification of chemical composition. Second is functional group analysis. Next is molecular structure determination. In addition, FTIR can be used to conduct quantitative analysis. Lastly, FTIR also can be used for characterization of functionalized materials. Now I am going to explain about the FTIR analysis sample preparation. The first step is sample selection. The second step is grinding process if applicable. The next step is the sample dispersion method using ethanol. The next step is sample mounting followed by pellet preparation using hydraulic press. Then surface preparation is conducted and lastly the samples will undergo drying process. Next, I am going to explain the characterization using FTIR of unknown sample 15. From the spectrum, the vibration modes of its constituent elements was observed from the range of 400 cm-1 to 3800 cm-1. Now, I am going to explain about the possible material of the unknown sample 15. From the FTIR spectrum, asymmetric stretching and angular deformation of silicon, oxygen, silicon vibration and sodium calcium phosphate bands were present. This FTIR analysis acts as an extra confirmatory analysis to further improve the claim that sample 15 is a ceramic tile. This is an overall discussion of the chosen material for samples 13 and 15. For the sample 13, after completing the FESIM EDX analysis, there are four possible materials which are stainless steel, nickel-based alloy, cast iron and carbon. open steel. In order to conduct the XRD analysis, only the stainless steel and nickel-based alloy is passed through. This is because the PCM EDX elemental composition shows that sample 13 must contain carbon and nickel material. After that, from the XRD analysis, only the nickel-based alloy will go for Raman spectral analysis because the stainless steel must contain a high percentage of chromium compared to nickel. So lastly, we gather the supporting data from Raman analysis which support that the sample 13 might be a nickel-based alloy. For sample 15, after completing the PCM EDX analysis, there are two possible materials which are ceramic tiles and porcelain tiles. Both materials are passed through the XRD analysis. After that, from the XRD analysis, only the ceramic tiles go for Raman spectral analysis and FTL spectral analysis because the porcelain tiles do not contain the iron oxide material, but the ceramic tiles contain the iron oxide as identified from XRD analysis. So lastly, we gather the supporting data from Raman and FTL analysis which support that the sample 15 might be a ceramic tiles. As a conclusion, in this project, the mechanical properties were not examined and analyzed, so the atomic force microscopy (AFM) can measure the mechanical properties such as performing nanomechanical measurements, materials hardness, elastic modulus, or frictional properties. In summary, AFM analysis plays a vital role in characterizing the surface properties, topography, defects, and mechanical behavior of ceramics materials and nickel-based alloys. Another analysis is differential scanning calorimetry (DSC). DSC analysis can measure various thermal properties of materials including specific heat capacity, thermal conductivity, and thermal diffusivity. In summary, DSC analysis is a valuable tool for understanding the thermal behavior, phase transitions, kinetics of reactions, and thermal properties of ceramic materials and nickel-based alloys. And that's all from us. Thank you.